Let's talk about adiabatic process in this class. Well, we do have talked about this, but not in a very quantitative way. All we know about adiabatic process is that the net heat pumped in the system or net heat involved is zero, which basically means that if you know that from first law of thermodynamics, dq equals dE plus P dV, where P dV we already know is the work done by the system. We know that dq is zero for an adiabatic process. Okay, what is dE? dE is a change in the internal energy of the system. If you provide energy to the system, the temperature of the temperature of the system increases, and we know this from specific heat, that specific heat is the is a measure of how much temperature increases as we as we do some work on the system, or as we do provide some energy to the system. So basically, dE is going to be CV dt, um, which we have actually talked about in the last class. And for adiabatic process, this reduces to CV dt plus P dV. Now, we actually want the equation of the state of the system, which usually is in terms of P and V. We know that for an isothermal process, PV is a constant. That's the equation in terms of P and V. This is isothermal. We know that for isobaric process, just P is a constant. And we know for an isochoric process, just V is a constant. Now we want to do the same thing, obtain similar kind of equation in terms of PV for an adiabatic process, and this is our starting point. So we can use equation 1 to find the well, actually not equation 1 but here, to find the equation of the state of the system. Now we see it involves D, it involves P, it involves V, and we want this equation in terms of PV. So to do that, we know that for any process, PV is an RT. That always hold true for an ideal gas. So we can sort of make differential of this and differentiate it. This is what we get. And now, as you can see, that we can use equation 1 and 2 to remove T. How can we do that? Well, we know that for an ideal gas, R is Cp minus Cv. Cp is nothing but the specific heat at constant pressure. Cv is the specific heat at constant volume. And we also know that there is this is called gamma, and this is 5 over 3 for an ideal gas. We're talking about ideal gas right now. Okay, with this we can write P dV plus V dP R over Cv P dV. Using equation 1, 2, and 3, you can see the following equations will come. And we can write dV over V plus dP over P equals minus of Cp minus Cv divided by Cv dV over V equals 1 minus gamma dV over V. Now we can simplify it further to look like this, and we can integrate that. We know the integral of this is ln P plus gamma ln V equals a constant. So basically, you integrate here from P1 to P2, and similarly here from V1 to V2. Okay, What does this give? This gives us PV to the power gamma equals constant. This is the equation of state of the system for an adiabatic process. How does it look? Well, if you draw a pressure volume diagram, then if you draw two isotherms, which means isothermal processes, this is T1, this is T2, and then your adiabatic process is going to look like something like this. And well, let's make it look better. So it's going to look like something like this. Okay, here T1 is greater than T2. So as you can see, the system starts at some temperature T, and it loses energy and because of that it loses temperature and reduces to a lower temperature T2. In the process, it does some work because there is no heat pumped in. All the work done is actually coming from the internal energy. This is the work done. We know that dW equals PdV. So we know W is going to be integral of PdV from volume V1 to volume V2. This is volume V1 and this is volume, well actually this is volume V2 and this is volume V1, V2. Okay, well, yes. So, well, I should be the other way around. I'm sorry. This is V1, this is V2. Okay, this is the work done. We know for isothermal process, just to complete the whole thing, if you draw an isotherm, then for an isothermal process, if you start from V1, V2, this isothermal, we know it's going to be dW equals PdV. For isothermal process, PV equals a constant, then PdV plus VdP equals 0, and then you can actually calculate. We can have a lecture on this, but it's just a matter of integration, finding PdV. So that was just work done for the adiabatic process. So let's talk more in the following class.